Hi everyone, thanks for joining us today. My name is Jeff Winter and I'm going to be talking to you about safety bypassing. Based off the high turnout today, I actually think it confirms that this topic is on a lot of people's minds, and therefore I'm quite excited to be talking about this. The goal of the presentation is to give everyone better insight into a traditionally taboo topic so that you can either improve your safety in areas where you didn't know were high risk, or improve your productivity in areas where safety may be overly restrictive, or potentially both. Before getting started, it might be relevant to share a little bit about myself. I'm the director of Grantek Safety Practice, which is a small team within the company dedicated to being subject matter experts on safety. We're basically tasked with providing guidance internally to our engineering teams and externally to our customers. It's important to know that our group doesn't just dabble in safety. We're committed to being true leaders in the field. We do more than just read up on what is current. We actually spend time getting involved so that we can help contribute and improve the industry. And because this topic of bypassing has been a big talking point in several of my industry committees and also turns up on our projects quite frequently, we thought it would be a great way to share what we know. We'll publish this webinar on our website after we're done, and all the attendees will be emailed with a link to the recording. Because of that, everyone's lines will be muted throughout the entire presentation. Therefore, if you have any questions throughout the presentation, you'll need to email me directly, and then at the end of the presentation, I will address all the questions that have been sent to me. This keeps everything running smooth for all viewers. My email is jeff.winter@grantek.com, and it'll be posted several times throughout this, just in case you need a reminder. So when we talk about bypassing, we first need to start with defining what bypassing is. So we're all speaking the same language, which, as you may learn, is not so simple. Then we'll look into the process of determining when and where bypassing can be used. We'll discuss the current industry requirements as well as a few common mistakes. And at the end, we'll wrap up with an example of a solution that we were a part of implementing. So let's start with a painfully obvious yet, yet potentially difficult question to answer. Is bypassing good or is it bad? Well, depending on who you talk to, you may get a variety of different answers. Some may say, of course it's good. There's no way you can perform your job if it weren't. Whereas others may say, no way, Jose, bypassing is always bad, period. So who's right? Well, without a common definition, understanding of what bypassing truly is, potentially both are right. Here are a list of the most typical terms associated with bypassing. You have bypassing itself, defeating, overriding, disabling, suspending, and even a commonly confused term called muting. Regardless of your background, your understanding, or your experience, without defining these terms, not everyone will come to the same understanding as to the ones which have good connotations and the ones that have bad connotations. And that is a major problem. We all need to be on the same page before we can move forward. You may think we are diving into the weeds of semantics here, but miscommunication and misunderstanding of these terms can lead to huge risks, unnecessary liability, and ultimately lead to a very unsafe work environment. This is currently a big problem in the industry, and some of you may have already recognized it, whereas others will learn about it for the first time in this presentation. So what does OSHA, the regulatory body in the United States, have to say about these terms: bypassing, defeating, overriding, disabling, suspending, and muting? How I approached this, so you're aware, was I literally used Control F for find and searched for the terms that I just mentioned. So if we take a look at Part 1910, Subpart O, which spells out the requirements for guarding, the only time any of those words exists is for a very specific requirement around mechanical power presses with muting, where bypassing is actually used in the definition of muting. So muting is sort of defined, but bypassing isn't. That's it. So let's jump over to Subpart J, where control of hazardous energy requirements reside. What does that have to say? Almost nothing. I mean, there's only one small reference to the term bypassing, which says, if safeguards are bypassed, then lockout is required. So we don't really know what bypassing is here, but whatever it is, it's not allowed. Last spot I was able to find any reference to any of the terms related to OSHA is actually in a 136-page field directive given to OSHA inspectors for how to enforce 1910-147 or lockout tagout. To be clear, this isn't a regulation, it's just a guide. Bypassing is mentioned 7 times and defeating 4 times. Neither are defined, and yet they seem to be inconsistent on which word they use where, making it kind of confusing. In all cases, however, the general takeaway is bypassing and defeating are both bad. So if you use OSHA as your source, we have learned anything here? I don't really think so. Do we even know what bypassing is? No. All we know is that it appears to be bad. So OSHA wasn't much help. Let's take a look at the industry. What does the industry have to say? ANSI B11.0 and B11.19 are the 2 most universally used standards in the United States, so let's start there. B11.0 explains the general requirements for all machines, mainly revolving around the risk assessment process. And in the standard, none of our words are defined. However, there actually is an entire section specifically called removing, disabling, bypassing, or suspending of safeguards. Now, once again, it doesn't define any of them, but it essentially says that no matter what you call it, it can be used under certain circumstances with proper precautions. Go see B11.19 or Z244.1 for help. So let's jump to B11.19 then, which is the standard that says how to apply, install, and use guards and safeguarding devices. Well, look, we at least have our first definitions now, but only for 2 words, bypassing and muting. Bypassing is rendering ineffective any safety-related function of the control system or safeguarding device, and muting is the temporary automatic suspension of a safety-related function. So how do these definitions sit with you? Do you think you clearly understand the difference or have a good handle? Well, let's keep going. So B11.19 does have a section dedicated to bypassing and one dedicated to muting, explaining what is required when they are used. That's great. The only problem is, we just went over, OSHA said that bypassing isn't allowed. So what do? Well, we'll talk more about that later. Let's continue along with some of the other big standards that most people use, starting with ANSI ASSE Z244.1, the newly revised standard on control of hazardous energy, which focuses on lockout, tagout, and alternative methods. It is those alternative methods that are relevant to our topic of bypassing today. So this standard has an entire section on alternative methods, yet there is no mention of any of the words we have talked about so far, except under the return to service area, where it gives you requirements after you're done locking out, and all it basically says is that your safeguards that may have been disabled, removed, or bypassing have to be reinstalled and functional before operation. That's it. That isn't really that helpful, and it doesn't really kind of apply to the way that B11.0 explains that this would help you answer it. So now let's look at NFPA 79. This standard primarily deals with electrical system design for all machines, and different parts of it bleed into machine safety. So NFPA 79 states that defeating and bypassing are both not allowed. However, it says overriding safeguards can be allowed at certain times, and then spells out some of the requirements. So great, this is just what we need, another new word. So now let's look at RIA R1506, the safety standard for robots. Interestingly enough here, the terms bypass and muting only come up in the section for verifying and validating your system. And all it says is that you need to make sure that your bypass and muting functions are correct. Whatever they are, just make sure they function correctly. That isn't too helpful. However, they do have an entire section called suspension of safeguards, which is very similar to ANSI B11.19. They just use a different term instead of bypassing. And I don't know if you're starting to recognize this, but this might be getting a little confusing, wouldn't you say? And that's why I want to keep going with this. So let's keep going to some of the international standards and see what they say, starting with ISO. So ISO 12100 is the international equivalent to ANSI B11.0. So if you buy equipment overseas, chances are they follow this one. It's very similar. There's only subtle differences, of which, to our luck, the nomenclature of bypassing appears to be one of those differences. One section states that protective devices shall not be bypassed, but later in the document it says some protective measures may need to be suspended for certain tasks. Even though this is conceptually the same as B11.0, using different words can have a big impact on a machine builder trying to communicate with their customer about potential bypassing capabilities. Next is ISO 13849-1, the most popular standard worldwide for how to design safety-related parts of control systems. Only muting is mentioned here with the same definition as ANSI B11.19. But says if you happen to design a system that suspends protective devices, be sure to tell the user. Thanks 13849. That's a big help. So lastly, let's look at CSA, which essentially mirrors the language and requirements of the two ISO standards I just mentioned, so there's nothing really new here. So in summary, there appears to be a bit of inconsistency in language, making it very difficult for the average safety person or average engineer to really know if what they are doing is right or wrong, allowed or not allowed. It can also be really hard to look up answers if you don't know what words to search for. Imagine if you read ANSI B11.0, which says bypassing is allowed, but you're purchasing a machine from a company that follows ISO 12100, which says bypassing is bad. Neither of the standards define them. What happens? How would that conversation go? So, because of this confusion in something as simple as a word, there can be some major unintended consequences, and that's what I want to be talking about here. First, if bypassing as a concept, regardless of your word choice, is not built into your risk assessment and risk reduction process, you will inevitably find employees who develop workarounds on your safeguarding solutions so that they can get their job done. And this is really, really bad. Not only is the employee in this situation exposed to very high levels of risk, but if they don't remove their workaround, whatever it is when they're done, all future employees might not know that those safeguards have been defeated, leaving an illusion of safety. In addition, if someone were to get hurt with a safeguard defeated, you're going to be in a very uncomfortable position with OSHA. This could go from a serious violation to a willful violation, potentially 10 timesing your fine amount. So you're not only creating more danger for your employees, but you're also adding more financial risk. Once again, really bad. Second, if the concept of bypassing isn't clarified and agreed upon by all stakeholders in the company, mainly engineering and EHS, chances are you will have equipment that may currently be capable of bypassing some or all safety functions, and you might not even know it. Even worse, it's inconsistent between machines. Nearly all the equipment Grantek works on has more than one operational mode. There's typically a run or automatic, accompanied with at least one other mode, like a manual, maintenance, sanitation, jog, teach, setup, or something else. Regardless what it's called, how familiar are you with its functionality? Do any of these modes essentially act as a bypass, turning your safeguards off, even though they aren't labeled as such? And if so, how do you know? So Grantek did an experiment in 2015 that evaluated 8 different machines connected together in a brand new production line. In this case, all equipment came back as compliant to industry standards and arguably safe when looked at individually. However, we noted that 3 of the machines had operational modes which did in fact bypass safety functions. Remember, according to ANSI B11.0, that's allowed. In each case, they were labeled differently and functioned differently. 1 being called setup, and 2 being called maintenance mode. The engineers seemed to understand how they worked, but the safety teams had no idea in this case. So as a safety professional for your company, how difficult would it be for you to implement and manage a safety program if you don't even know there are bypassing capabilities currently built into your equipment? How do you train your people? So all that being said, what should we do? What should you do as an employer? The very first thing I recommend as an organization is to define what is good and what is bad. Pick terms that resonate with your company and ensure everyone is on the same page with the use of those words. In my case, I personally like the word bypassing as being associated with good or allowed. Some of you may hate the word bypassing or cringe when you hear it. That's fine. Just pick a word that works for you. Whatever the word is, define it and make sure everyone accepts it. In this case, I like the definition of the manual suspension of a safety function or safety device. This is not to be confused with muting, which is also allowed and good, but defined as the automatic temporary suspension of a safety function or safety device. The major difference between bypassing and muting here is automatic versus manual. If your machine automatically suspends a safety function, you're muting. If someone manually flips a switch, you're bypassing. Both okay, but know the difference. Now here's where most companies go wrong. They forget to define the bad or not allowed concept. I like the word defeating as my not allowed concept, and I like to define it as an intentional and unauthorized act which renders a safety function or safety device ineffective. So now we have a clear distinction: something good sanctioned by your company and something bad forbidden by your company. Most safety standards or regulations, as you've learned, don't really define these, and if they do, they don't differentiate easily or consistently between what is allowed and not allowed. These are the two I recommend. You are welcome to pick other ones, but pick a good and a bad. And now that you have a good and a bad, you can associate all other nomenclature and regulations and standards to fall under your terms. It doesn't matter what others call it, as long as you can relate their good terms and their bad terms with your good terms and bad terms. At least for the remainder of this presentation, we're going to associate bypassing with good and defeating with bad. So a second thing, as an organization, you will need to determine where you allow bypassing and when it can be used. If you don't come up with an authorized and approved way to bypass safeguards, your employees will find workarounds. They will defeat safeguards. I guarantee it. They will have no option but to defeat. And chances are engineers and EHS will differ on when and where bypassing can be used, so make sure everyone is on the same page. Third, once you determine when and where bypassing can be used, make sure both design and functionality or functional engineering requirements are established and agreed upon. The last thing you want is to have inconsistent bypassing functions across your organization. A big one here is to specify or clarify is which operator modes have bypassing functionality. Maybe maintenance mode or setup mode is what your company likes and allows to have safety bypassing capabilities. Whatever it is, pick one and make sure your machine builders, your engineers, your maintenance, your operators, and everyone knows it. It is far less expensive to force the machine builder to change the nameplate of an operational mode to be consistent with your company's requirements than it is to attempt to manage a safety program with potentially hundreds of variations of operational modes, of which some bypass and others don't. So now that we've defined what bypassing is, let's talk about when and where you can use it, or more appropriately, how to figure that out. So where does one start if they want to entertain the idea of using bypassing on their machines? The starting point is always the risk assessment and risk reduction process, which in the United States is described in ANSI B 11.0, in Canada the equivalent to CSA Z432, and in Europe it's ISO 12100. Conceptually, all standards are very similar in how they approach the risk assessment and risk reduction process. No matter how you approach the process, the goal of these standards is to reduce the risk to acceptable levels. So I'm going to go over the basic process of the risk assessment, but tailor it to the idea of bypassing your safeguards. I'll be using ANSI B 11.0 as my basis of discussion here today, but please note that this concept applies to all the other standards I mentioned as well. So the first two steps of the risk assessment process are to identify tasks and hazards and to estimate risk. I like to break these into discrete steps for easy understanding, but honestly, most people just do steps 1 and 2 simultaneously. So you start with hazard identification, identifying all the possible areas you could get hurt by a piece of equipment. We aren't yet evaluating the risk, just identifying the hazards. The reason I like to do this separate is because it helps ensure that all hazards are evaluated, not just those that have tasks associated with those hazards. So far, bypassing doesn't apply yet. We're just laying the groundwork. Then you identify tasks and estimate your level of risk. This is the real meat of the risk assessment, evaluating the probability of injury to calculate risk levels. Older risk assessment processes estimate risk solely based off the hazards, not including tasks, like the one here on the left that you see. These assessment types are simple and sufficient for general safeguarding, but they really can't be used if you want to implement any type of bypassing. In order to do bypassing correctly, you will need to conduct a task-based risk assessment, which identifies all the tasks involved with interacting with the equipment, not just operational tasks, but also maintenance, sanitation, quality, anything and everything someone has to do to or with the equipment. This will help avoid defeating because you're aware of how people need to interact to perform the particular tasks. Now, as part of this task hazard evaluation, don't just document what people currently are doing and then estimate the risk. You really need to understand what employees are doing and why. Why are they getting into the machine for certain tasks? Or even worse, why are they currently defeating safeguards? Is it really necessary? Could it be because of bad safeguarding design or possibly laziness or something else? If you don't investigate the actual ways people perform tasks, you'll never know. So now let's take this one step further. I like to call this step 2.5. Even if you did a great risk assessment and came up with a great safety solution that includes bypassing, you don't want to be caught off guard by one of the simplest yet most overlooked questions out there. A question that undoubtedly your OSHA inspector will ask. So, that nifty safety system is great, but why didn't you just lock out? So this is where machine safeguarding meets lockout tagout. Two different regulations in OSHA and also two different standards in the CSA, ISO, and ANSI worlds. In the case of ANSI, you're directed towards ANSI ASSE Z244.1. Like we mentioned earlier, it's an entire standard dedicated to the control of hazardous energy for times when you need access to equipment above and beyond just normal safeguarding. This table I show here on the right is an example of a set of questions from Z244.1 and OSHA to help you answer, can or should I even allow bypassing as an option for this task? You want to make sure that people don't start conducting risk assessments and offering a bypassing solution on every task just because it's easier. You know, kind of thinking, sure, go ahead and add a bypassing switch there. I'm sure they will use it for something. I mean, there's always something that goes wrong. That's not really what you want to be thinking. You want to have limits around it. So make sure you go through this exercise or one similar to it to help determine which tasks require lockout, which rely on the safeguarding you put together, and which allow for bypassing. Now, going through all that, let's assume that the task warrants the use of bypassing. You have agreed and decided that the operator has to get in the machine for a task. So let's talk about the correct bypassing solution, how that is determined. Surprisingly, this process is actually fairly straightforward. You follow the general control hierarchy that is published in most standards, starting with inherently safe design measures, then engineering controls, and lastly, administrative controls. There's actually no real difference in coming up with a normal safety solution and a bypassed safety solution. All that really matters here is that you do, in fact, apply this control hierarchy to your bypass solution. You don't just say, we added bypassing and it shuts everything off. Mr. or Mrs. Operator, just be careful. No. You need to ensure your bypass solution still goes through this process to find a way to provide adequate protection. There are actually a lot of options or combination of options that can be very successful. Remember, the process is the same for selecting your bypass solution as it is for selecting your normal, everyday safeguarding solution. Throughout this process, it is imperative that you evaluate the residual risk that will be left over, especially when a safeguard is bypassed. In some cases, You might be able to keep the risk at a super low or negligible level, whereas others, you might be left with a higher level of risk, which your company will have to determine if that's appropriate level or not. But don't skip the step of residual risk for your bypass solution. Be sure to evaluate it. Now, if the risk is not acceptable, you go back through the risk reduction process on the previous slide and figure out what else you can add or do to make sure that person performing the task is protected enough and the risk is low enough for your acceptability. So after going through this process, and keep in mind the process is essentially the same on new equipment as upgrades of old equipment, you then tie this new safeguarding solution into your EHS programs and policies to ensure proper use. It's no use having a super awesome state-of-the-art solution that bypasses safeguards if your company isn't prepared to use it. Think about the training and procedures that are needed to support it. Bypassing solutions, as we previously defined, are manual by their very nature and therefore require a human to make a decision every time. So your administrative controls are critical to a successful bypassing implementation. You definitely don't want someone using bypass as a concept or a bypass switch incorrectly, especially if they don't even know how it works. No pun intended here, but that defeats the purpose. So, at a high level, we went through the process for how determining bypassing fits into a risk assessment process. So assuming you've decided to use it, how does it need to work? So ANSI B1119 is the only standard that has a section dedicated to the performance requirements of bypassing. So once you decide you need bypassing, this is the main standard that tells you how it must perform. The first requirement is the simplest in concept, yet probably the most overlooked. When you bypass a safeguard or safety function, you have to have something else there to provide protection. Like I kind of alluded to earlier, you can't just have a bypass switch that just shuts off all safety devices with no rhyme or reason and with no other means of ensuring people are safe. There are two general types of categories for how people address this. The first is alternative safeguards, and no, this is not like alternative facts. Very simple, when you turn one safeguard off, you need to turn another one on. Basically, all of the devices listed in ANSI B1119 qualify for this, whether it's light curtains, interlocks, laser scanners, you name it. For example, when you bypass your interlock guard door, a laser scanner on the inside would be turned on, or an enabling device with a hold to run would now be required. In either case, one thing shuts off and another one is now used. Protection is still being provided, just differently. The other method for achieving this requirement is through supplemental devices. You could think of these as complementary to the primary safeguards, trying to help further minimize the risk. They're meant to be used in conjunction with something else. This is really where things like safe motion capabilities come into play. IEC 61800 spells out about a dozen or so different flavors of safe motion, the most popular for bypassing being safe limited speed. This is a way your safety system can ensure your machine is in its bypass mode doesn't exceed a certain speed. Now, you might be thinking, yeah, what speed? Well, just like all other safe motion technologies, there is no absolute requirements for what is safe. Your risk assessment should help determine what a safe speed or a safe position or safe direction or safe torque, whatever is appropriate for your application if you choose to use these technologies. Now, that being said, a general rule of thumb adopted by the robot industry is that mechanical motion at 10 inches per second is considered a safe enough speed to lower the probability of injury to a low level. So we like to use that as a good starting point. You should have one goal in mind here. Just work through a solution that provides other protective measures to ensure the employee is safe performing their task. The second requirement to bypassing is to ensure that emergency stop functions always remain active. No exceptions. You can't bypass your emergency stops, period. I don't think that people aim to bypass their emergency stops, but depending on how you wire your safety circuit, you can very easily accidentally bypass them as part of your bypass. Let's look at an example here. Fairly recent picture I took of a machine. In this case, the safety relay inputs were jumpered out, or to use our new term, defeated. Clearly unauthorized and unacceptable. The intent here was to jumper out the interlocks. But the unintended consequence, however, is that the emergency stops were also jumpered out and no one knew. Can you imagine needing to hit the emergency stop and it doesn't work because someone tried to defeat or jumper out the interlocks? Now, if you had a proper bypassing circuit, this situation would never occur. The third requirement is to ensure that the bypassing functionality itself has the same circuit performance as the function it is in fact bypassing. It's sadly all too common to have a very nicely designed safety circuit, such as an interlock wired into a safety monitoring relay with redundant contactors all being monitored, say category 4, performance level E, the highest out there. And then you add a bypass switch that bypasses the interlock, but yet it's just a single channel selector switch with no monitoring, and when you do that, it makes the bypassing function the lowest possible out there, category B or performance level A. So in this case, you've essentially destroyed the integrity of the whole system by introducing a weak point, your bypassing switch. So make sure you include all parts of your bypassing hardware as part of the overall safety function to avoid these mistakes, and then verify and validate accordingly. Hold your bypass design, the design of your bypass, to the same level as the rest of your safety. Another requirement is that bypassing functions must be capable of being supervised. Essentially means that any old bystander shouldn't be able to come up and bypass the safety. Realistically, the way that most companies do this is through physical keys or passwords on HMIs. Some more advanced systems use RFID tags, where certain individuals have different levels of bypassing. For example, operators have a basic level, maintenance teams have a higher level, and you could even set it up so the plant manager is the only person to have the highest level of bypassing. In theory, you could also do this through a very well-managed safety program where you create a series of authorized users, but that just may be more work than adding a key. Next, there needs to be some readily and easily observable indication that the machine is in a bypass mode. This is most commonly achieved by either a strobe light or modified stack light with a specific light for a bypass signal. This could also be some sort of buzzer, or it could be both. The idea here is that everyone, especially the person working on the machine with the safeguards bypassed, is aware that the safeguards are currently being bypassed. Typically, this is accompanied with administrative controls where employees know what to do, or more importantly, what not to do, if they see a machine in bypass mode. The last requirement I like to bring up is that of making the bypass function temporary. Now, interestingly enough, this requirement is not in ANSI B 1119, but however, it does indirectly show up in NFPA 79 for their bypassing, which remember they call overriding. And of course, NFPA 79, in that standard, temporary is not defined. That is up for you to pick. I highly encourage, as part of your risk assessment process, that you determine an appropriate amount of time that is allowed for the bypassing function. How long should it take to perform the task? 10 seconds? 10 minutes? 10 hours? It honestly doesn't really matter as long as it isn't arbitrarily chosen. The goal here is to prevent a safeguard from being bypassed forever. So, in total, if you follow the risk assessment process we have described earlier and follow these 6 design and functionality requirements, you're in really good shape. You will have successfully built a safety system that protects your people, yet still allows them to do their tasks and does not encourage them to defeat the safeguards. Also, you'll have come up with a universally understood concept that can be easily explainable to your employees and to the authorities if need be. So we've gone over the main parts of bypassing so far. Let's start to look over some of the common mistakes that we see out there. So the first and most common mistake we see is a well-designed safety system that gets destroyed by introducing a PLC to control the bypassing portion. This is very prone to occur in systems where there's only a safety monitoring relay and not a more advanced safety controller, safety PLC. If all you have is a basic safety monitoring relay, it can be pretty tempting to add the use of, to use the existing PLC with the existing operator interface buttons to add a new bypassing capability, kind of like what's captured in the picture here. The only problem is in doing so, you weaken your whole safety system to a point where it's actually not worth even having the safety monitoring relay at all, and we don't want that. In most cases, it's easiest to replace your safety monitoring relay with a safety controller where you can build your bypassing function directly into the safety system. Another common mistake we see is how the means of bypassing is wired into your safety circuits and controlled through your logic. There are two types I want to discuss here, and both of them assume that correct safety hardware is used. It's just applied incorrectly. So these are examples where you're not using the PLC. You just happen to still be doing it wrong. The first one I want to talk about is designing parallel circuits. So this is when you hook up two safety devices to one set of inputs on your safety monitoring relay or your safety controller. And if either one of them is good, the safety circuit is good. Unfortunately, parallel circuits eliminate the system's capability of properly doing fault detection, meaning you can't achieve a circuit architecture higher than category 1 with this design. Essentially, using a parallel circuit design is a big no-no all around. Like, you shouldn't do it anywhere in safety. This method just happens to show up more common when you're implementing bypass circuits. Now, the second of these two I want to talk about is using OR logic in programmable safety controllers. Remember, in this case, I'm not even talking about using regular old non-safety PLCs here. I'm talking about using very reliable, very good safety controllers. You just might be using them wrong. So functionally, an OR gate is the same as parallel wiring. If either input is good, then the output is good. The difference between parallel wiring and the use of an OR gate is that an OR gate has the ability to maintain high levels of diagnostic coverage, meaning it's possible to still achieve a circuit architecture of category 4. A parallel circuit won't catch a failure, whereas an OR gate in a safety controller can. But just because your circuits can detect faults and be category 4 doesn't mean you designed your bypassing correctly. Now, don't get me wrong, OR gates are awesome and absolutely have a valuable place and use. Just be extremely cautious when deciding to use them for bypass circuits. It's all too easy for an engineer to think, oh, an OR gate is perfect. If this switch is turned on or the door is closed, then the machine can run. So the operator can do his job. Boom, we're done. That's not really the way that you should be thinking about it. An OR gate by itself doesn't provide all the necessary logic you may need to ensure all of your safety conditions are met before you can use bypassing. It's rarely ever as simple as either of these devices can be good and everything is safe. In nearly every bypassing circuit I've been a part of, there typically are quite a few logic blocks that come together to ensure the exact desired scenario is met before bypassing can begin. So although it may be possible to use an OR gate, I'm not saying never, it's just very easy to do it wrong. Please ensure that you use a truth table with all outcomes where they're all considered. You're going to find out that you're most likely going to be using an XOR logic instead of an OR, and you're probably going to be adding a few others like AND gates as well. Another common mistake we see is having a bypass circuit designed into a machine that is arbitrarily made and not tied to any particular need or task. Essentially, with the mentality of, well, we don't know what can go wrong, so let's just build a bypass switch that turns off all the safety devices. Now, in theory, there's nothing that states that a bypass can't turn off all safety devices, but if you do this, you're most likely going to have people using bypass for things that they shouldn't be using it for. So I highly suggest selecting certain safeguards that are bypassed specific to the tasks that need them. The bigger problem we see is more associated with the mentality of bypassing. That bypassing doesn't really need to be a part of the risk assessment process because it's meant to be the catch-all for things that are unknown or incapable of being planned for. And that is the type of thinking that will get you into trouble, not only resulting in a poorly designed safety system, but also poorly implemented administrative controls. It's really hard to train people to be safe when their only option is to turn off all safety devices. Take a look at the data on the right here from INRS, a German research group who was seeking to find out when and why employees are tampering with the safety devices to perform their tasks. These were the responses to surveys filled out by employees who were in companies where accidents had occurred. Every answer you see here is an example where an employee stated they needed to defeat the safety. They had no other option in order to perform their job. Now, some are more obvious than others, such as setup and troubleshooting, but the point is, if you don't factor in the true needs of the task to operate and maintain the equipment, people will find workarounds and defeat the safety system to get their job done. This data here proves that people do it all the time. In this case, find out what people do for setup and what they do for troubleshooting. It's very easy to design bypassing solutions that allow you to do those tasks and do them safely. So we have quite a few examples of different solutions, but time limits us to just one for this webinar. So if you'd like to discuss your application or see other ideas, feel free to reach out and we can discuss. But that being said, I'd like to go over my favorite example. So this project happens to be one I like because a bypass system already existed, but was just in desperate need of an upgrade. So this not only addresses what a good solution will look like, it also highlights what a bad bypass can look like. So this machine was a Krone Solomatic Labor, probably 20 years old, I'm guessing. It runs 24/7, 365 days a year continuously. When it's running, it goes around 15 or so RPM, which translates to about 30 or 40 inches per second. The guarding was pretty haphazard and definitely insufficient. You can tell it's been modified and adjusted over time. Like I mentioned a second ago, the machine had a bypassing solution, which happened to be a 2-position pendant, which is also known as a dead man switch. And for those of you who don't know, a dead man switch is very antiquated technology, and as its nickname implies, it wasn't too effective. So the bypass switch, when used, ignored all safety systems on the machine, allowing the machine to continue at full speed. In addition, the circuit performance was very poor, all being controlled by a PLC. There was no safety monitoring relay anywhere in there, making the whole solution very unreliable. So knowing this, I mean, how does this make you feel if you had an operator who's relying on that bypassing solution to keep them safe, but it's not really doing much protection at all? So the first thing we need to do was to conduct a risk assessment. And in this case, we did find that there was a task that required access to the equipment while it was running. At least once a day, at a minimum, they have a setup process where they need to apply new labeling and unclog the new labels as the machine is starting up. In addition, we found out that their sanitation team needs to get in there daily, and having the ability to rotate the machine while cleaning would save a tremendous amount of time. So we consider that task a necessity too. Now, these are some other questions you could ask. Do they need to bypass all the guard doors? The answer is no, just one. There's only one spot where they need access. Another question, do they need the machine to run at full speed? Definitely not. In fact, the task is actually easier if it is running at a slower speed. So this happens to be an example of what our detailed risk reduction plan looks like on this machine. The way that we approach it is we call out every possible safety requirement that is critical for an engineer to know so that they can design and build exactly what is needed. In this case, we use yellow to call out safety devices, green to call out mechanical guards, and orange to call out operator interfaces. Even without knowing what the heck any of these things are, you can at least tell that there are quite a few items which need to be specified in order to make this all come together. Remember, we aren't talking about the total safeguarding solution, only the one task which includes bypassing as part of the solution. So on the right here is an example of the amount of detail that goes into just one of those call-out boxes on the left. It's a lot. So instead of boring you with every little detail, I'm going to describe the gist of it on the next slide. But the takeaway here is that if you don't spell out the details, someone, somewhere, will have to make assumptions about the answers. And it would be very coincidental if the designer's assumptions match your assumptions. So you really need to clarify everything. I would anticipate several pages at least for a good description of a bypassing solution. So let's look at the solution. So we replaced the dead man switch with a proper 3-position enabling switch, which requires the operator to hold the switch in the middle position. So either squeezing or letting go will shut down the system. This switch was kept in a lockable box so that only certain people had access. We added a guard locking interlock on a new door to the area that they needed access, and you can see it in the picture in the middle. In addition, we added zero speed detection and speed monitoring devices along with a cradle interlock to detect if the enabling switch has been pulled out of the box, all of which are controlled by a safety-rated smart controller. This is how the system worked in a nutshell. So in order for the operator to access the machine, they had to switch the mode to setup, which automatically brings the machine to a stop. It takes a couple seconds. So once the zero speed detection device detects stopped motion, the operator is allowed to lift the enabling switch off the cradle and hold it in the middle position. Once these conditions are met, the door unlocks, allowing access to the machine. There's a separate hold to run control that is used to start the machine operation back up, which in this mode is limited to 10 inches per second, or about a quarter of the original full speed. If any of these functions are completed out of order, or the machine isn't operating as it's supposed to, or it goes slightly faster than 10 inches per second, or a fault is detected anywhere in the system, the whole thing shuts down and requires the system to be fixed and reset. It's a pretty slick system. This, of course, was accompanied with the proper administrative controls, including warning signs, procedures, and training. Afterwards, residual risk was evaluated to make sure that the risk was still low, even using this system. So everything being said, the new bypassing solution was designed to allow an operator a safe way to perform their task while maintaining a high level of productivity. If you look at the alternatives, it either would be to build it wrong or to not allow it, which would force the operator to defeat the system. In either case, you really have an unsafe situation and are exposed to a lot of risk. So we do have a lot more information about the example I showed, along with other examples if you're interested. This was only meant to give a taste of what it could look like. We've covered a lot today, but hopefully you learned a few things about what can be applied immediately. And the biggest takeaway really is about establishing what terms you want to describe as an authorized act to temporarily turn off existing safeguards, and as well as determining what is unauthorized when forbidden. From there, we've given a high-level guidance on how to design it correctly. So with that being said, now it's time to see what questions you have come up. So email me any questions that you may have.